Okay, so this is the second video, and in this video we'll be covering on, let's see, let's just write it down. We'll be covering on electric fields. Okay, so another name is just electric field strength or electric field. Let's just jump into the problem, and then let's see what we can learn from from this problem. Okay, at a distance of r1 from a source charge. So let's say you have a source charge, right? A 2 microcoulomb test charge. So I have a very small 2 microcoulomb, and I have a distance between them of r1. Okay, experience a force of 2.5 millinewton. Okay, determine the electric field strength at r1 generated by the source charge. Okay, so in this particular case, in general, what we want to do is we want to look for the electric field, and the electric field is actually the force per unit charge experienced by the test charge. So if you were to look for the electric field strength, right, you simply divide the force, so 2.5 times 10 power of negative 3 by the charge of the test charge. So that's going to be 2 times 10 power of negative 6. Okay, so that's how you do it. If you key that into your calculator, what you will find is going to be, let's see, I have 1250 Newton per Coulomb. Okay, so this is just to emphasize that you can determine the electric field strength without knowing the charge of the source charge. I do not know what is the value of QS. I don't know that, but what I can do is I can take a test charge, right? A test charge that I know the magnitude of its charge, and I put it at some distance, and then I look at how much force that test charge experience. Again, I would like to emphasize that this charge, this charge is the test charge, the charge of the test charge, and then the force that it experiences. Okay, so this is a very simple problem one. After this we'll go into problem 2. So what we can say from here, the conclusion that we can make from here is that the electric field strength is actually equal to the force divided by the charge of the test charge. Okay. Okay, so previously what we did was we looked at, okay, I don't know the charge of this source charge, but what I can do is I can put a test charge and then measure how much force it experiences. And the result that we had was that the electric field is equal to the force divided by the test charge, the charge of the test charge. Now, we can extend from that to answer the second problem, okay, which is determine the electric field strength 2 meters from a 4 microcoulomb source. Okay, so how do we do this? I would like to reiterate the results that we had before, which is E is equals to F over Q. And I would like to remind you Coulomb's law, which is F equals to K Q1 Q2 over R square. Now, of course, we can slightly modify this equation to be K times Q test charge and Q source charge over R square. Okay, and if I were to just divide it, so let's say I have F equals to K QT QS over R square. If I were to just divide it by Q test charge, right, I'll just multiply that 1 over QT. Right, I can cancel out the QT, and this leads me to the next results, which is E is equals to KQS source charge over R square. Okay, so it's very important that the charge that we're looking at is actually the charge of the source charge, of the source of the electric field. So if we look at problem number 2, the source charge is actually has a charge of 4 microcoulomb. So if I were to calculate the electric field at some distance, I would be, okay, 9 times 10 power of 9, this is just K, and then I have the charge of the source charge, which is going to be 4 times 10 power of negative 6 over 2 square, because 2 meters, right? And if you were to calculate that into your calculator, what you will find is that the electric field 2 meters from the 4 microcoulomb source is actually, let's see, is actually 9,000 Newton per coulomb. Okay, so for every coulomb that the test charge has, it will experience 9,000 newtons. Okay, now again, I haven't touched anything about direction. I'm merely calculating the magnitudes of how strong, how much force one single charge of 1 coulomb is going to experience. Okay, I will deal with the direction in the next problem. Okay, so here we not only have to calculate the magnitude, but we also have to calculate the direction of the electric field. Information given is the distance from some source charge. So this is going to be Q source, all right? This is the charge of the source. Okay, so it's best to just draw out what we have, right? So I have the source charge QS, and then at some distance away. So the distance from this QS is going to be 1.5 meters, and QS actually has a charge of 4 microcoulomb. It is always just safe to assume that when we measure the electric field, we are using a positive test charge. So positive test charge. Okay, so since the source charge is also positive, positive will repel positive, and therefore if we think about the force, right, the force will be repulsive. Okay, and the good thing is, if we look at our equation beforehand, I have E equals to F over Q, which is just a vector multiplied with a scalar, right? We can deduce that the direction of E is the same as the direction of F. So then I can say that the direction of E, so let's just write it down here. Okay, let's just write down here. I can say that the direction of E will be away from source. And that solves the second part, which is direction of E. So this is the answer for the direction of E. So you always think about it, right? Using force as a reference point. If it is a repulsive force, it's going to be away from the source. If it is a attractive force, then it will be towards the source. We always refer back to the force. And of course, we can calculate magnitude. We can calculate magnitude by simply plugging it in into kq over r square, remembering that this q is actually the source charge. Then I will have 9 times 10 power of 9 times 4 times 10 power of negative 6 over 1.5 square. Then the magnitude of electric field, 1.5 meters from the 4 microcoulomb charge, is going to be 16,000 Newton per coulomb. All right, so there's two parts of this answer, or at least there's two parts to the answer to this question, which is the magnitude and direction. And here what we learned is that the direction of the electric field is going to be the same direction as the net force, or just the force. Okay, let's deal with electric fields from multiple source in the next part of this video. Okay, so now we want to look at multiple sources of electric field. Okay, so in this particular question, let's just read it out. The diagram shows 2-point charges arranged in a straight line. Determine the net electric field at point P if R equals to 0.5 meters, which is 50 centimeters, and Q is equals to 2 microcoulomb. Okay, so as before, what we want to do at point P is to imagine we have a positive charge. Okay, want to imagine what happens if we have a positive charge, and then what we're going to do is consider the interaction between that positive test charge with one of the sources. So here what I'm going to do is I'm going to consider the plus 2q. So I have positive charge and positive charge. That means my force is going to be repulsive. So I'm going to have E1 here in this direction to the right. And then second thing I'm going to do is I'm going to consider the positive test charge with the other source. All right, so positive and negative is going to be attractive. So then I have E2 pointing to the right as well. All right, so what I can say then is that the net electric field is simply going to be E1 plus E2. Okay, so then my E net, I can quite simply substitute the values. I can have K, and then I have, let's see, where was it? Yeah, okay, so E1 is from 2Q, so it's going to be 2Q over R square, and then plus Q over 1.5 R square. Okay, I would like to point out that I did not put a negative sign here. I did not put a negative sign there, because the negative and positive sign simply tells us the direction. Okay, so because I have already considered the direction here, I no longer need to do that again when I calculate it. Okay, so then what I can do is just substitute the values needed. So then I can have 9 times 10 power of 9, and then I have 2Q. Q is 2 microcoulomb, so it's going to be 2 times 10 power of negative 6, and then R square is just 0.5 square, and then plus 2 times 10 power of negative 6 over 1.5 times 0.5 squared. Okay, that means that if I were to key that into my calculator, right, I will find that the net force, the net electric field at point P is going to be 176,000 Newton per Coulomb, and that is going to be my final answer. Okay, and its direction is going to be towards negative Q. That's my direction, because it says that determine the net electric field. It doesn't say the magnitude only. So when it says, you know, quite plainly electric field, you will have to determine both the magnitude as well as the direction. Okay, so here we have a different type of problem. We still do have 2-point charges, just like the question before, but now we have it in the XY plane. In other words, this is going to be a 2D problem. Okay, so let's just read the question. The diagram shows the arrangement of 2-point charges. Determine the net electric field at the origin if Q equals to 2 microcoulomb and R equals to 2 meters. Okay, so as before, what we want to do is we want to consider, okay, what happens if I put a positive charge at the origin? Okay, so the first thing, let's consider the interaction of that positive test charge with the negative Q. So positive and negative is going to be attractive, so I'm going to have E1 in this X direction to the right. And then if I consider negative 2Q, again positive and negative is going to be attractive, so I will have E2 going upwards. Okay, so let me just calculate E1 first, right? So I have E1 is equals to KQ over R square, and I can substitute the values there. I can have 9 times 10 power of 9, and then Q is just negative Q, which is just 2 times 10 power of negative 6 over R square, which is 0.5 times 2 square. Okay, so in this X direction, keep in mind that E1 is the only electric field in the X direction. Okay, so in this X direction, I will have 18,000 Newton per Coulomb. Okay, so that's the first one. The second one that we want to consider is in the Y direction. Right, in the Y direction, I will have 9 times 10 power of 9 again. This is the Coulomb constant. And then I have the charge of the source is going to be 2 times 2 times 10 power of negative 6. And the distance between them is just 2 meters. So that's going to be 2 squared at the bottom. So then I can key that into my calculator and find that the electric field in the Y direction is 9,000 Newton per Coulomb. Okay, 9,000 Newton per Coulomb. Okay, now if I were to draw this in a sort of if I were to redraw this in a triangle, what I will find is that the length of E1 and then combined with the length of E2, right, it forms a triangle where the hypotenuse is going to be the E net. So then my E net is simply going to be the square root of 18,000 squared plus 9,000 squared square rooted. So then my net electric field at the origin is going to be 20.124 kilonewton per coulomb. I use kilo because it's easier than to write zeros. Okay, so that's the magnitude of the electric field at the origin, but we also need to find the direction, and based on our nice little diagram here, right, we can determine the angle. And if we were to look at the angle, right, it is the arctangent, so tangent -1, the opposite of the inverse tangent, right, inverse tangent of E2 over E1. So E2 is 9,000 and E1 is 18,000. Okay, so keying that into the calculator, what we'll find is that the angle is going to be 26.6 degrees. So 26.6 degrees. So these two, right, will be the answer to the question, right? Of course, 26.6, you should mention that it is the above angle from the x-axis, sorry, from the positive x-axis, because if I were to draw the net electric field on the graph, it's going to look like this. So it's going to be we will have the net electric field, and then we will have an angle here which is 26.6 degrees. Okay, so now we have problem 6, which is going to be the last problem in this video. All right, and this particular problem is quite interesting because it looks exactly like problem 5. The difference is in problem 5 we are asked to look for the net electric field, right? Whereas here we are asked to find the net force. Because we're still using the same source charges, right? Source charges, I will still use the same results from previously, which is 20.124 kilonewton per coulomb and the 26.6 degrees. That's just what I'm going to use. In fact, now all I need to do is really just imagine I have a charge here of 1 microcoulomb, right? So if I were to just find force, right, I know that my E is going to be equal to, let me just zoom in. There we go. Okay, so my E is just simply F over Q. What that means is that I can say that the force experienced by whatever charge that may be there is simply the charge of the test charge, which is the 1 microcoulomb, right, multiply with the strength of the electric field. Okay, and we can just do that quite easily. I can have 1 times 10 power of negative 6 and then times 20.124 times 10 power of 3, right? So let me just key that into the calculator. I have 20.124 times 10 power of negative, times 10 power of 3, and then multiply that with 10 power of negative 6. Okay. And so the force that I'm going to experience, right, is going to be, let's see, 0.02 Newton. That's 2 centinewton, okay, or 20 millinewton. 20 millinewton. And its direction, so direction is still going to be the same direction as the electric field, which is 26.6 degrees above the positive x-axis. Okay, so this is just a nice way of rounding up our circular sort of idea and relating the electric field that we've learned before to the Coulomb's law that we've also just learned, right? So these two ideas are very much interrelated to each other. If you know the electric field and you know the charge of the test charge, then you can figure out the force experienced by that test charge being placed in that electric field.